This is problem 46 from Chapter 6 of Randall Knight's Physics for Scientists and Engineers, 5th edition. We're not given a diagram, but we've got a description and some numbers. There's a truck on an inclined highway, 15 degrees. That's not very much. It's 7.5 metric tons, including the load. So that's quite a bit bigger than a passenger car, because I think a passenger car would be 2,000 or 3,000 kilograms at most. While this truck's going up the ramp, the load falls off. I'm going to pretend that the load is a heavy piano. After the load falls off the truck is when the truck begins to accelerate. So let me draw your attention to the word steady. If the truck is climbing the incline at a steady 15 meters per second, they're really implying that the velocity is not changing. In other words, the acceleration is zero, and that means we can set the net force equal to zero. But once the load falls off, now the truck is accelerating. That tells us that the balance of forces that was present previously has been thrown off. Now there's a net force, which means there is an acceleration. And from the information given, we're supposed to figure out what the mass of the load is. We're told to ignore rolling friction. There's no mention of air drag, which means we also ignore that. I made some slides for you. Let me find the pointer here in PowerPoint. Hopefully you can see that. Here's my truck with an upright piano on it. Obviously, this is silly because the piano's not that big compared to the truck, and it's not strapped down. Let's not worry about that. The total mass they told us is 7,500 kilograms. That capital M is the total mass, truck plus piano, and I'll use lowercase m for just the piano mass. So I'm not actually defining any symbol for the truck's mass by itself. That would be capital M minus little m. And I'm indicating this steady velocity up the ramp. Actually, to really emphasize that we're not accelerating, I would have to say something like a equals 0. Did I not do that? Okay, that's coming up in a later slide. With my blue bubble, you know I like to use these blue bubbles. That's in anticipation of writing F equals ma. I'm saying that everything inside the bubble is the m in F equals ma. We'll get to that in a second. So here's the beginnings of a free body diagram. They told us not to worry about air drag, so I didn't draw that. They told us not to worry about rolling friction, which would point opposite the velocity, down the ramp. So all we've got is the gravity, of course, pulling down. There's the ramp, or the highway, I suppose, supporting the truck normally along the normal axis, so we call it the normal force. And then there's this friction force between the tires on the wheel and the roadway. And as I like to point out, excuse me, these two forces, N and F, are really two components of one interaction between the tires and the road. So overall, the roadway is pushing that way on the truck, up and to the left diagonally. But we like to resolve that force into components. The component that's parallel to the roadway, we call it friction. And the component that's normal, we call the normal force. Your book might have put a subscript S here because it's really a static friction force. These tires are not supposed to be skidding. They shouldn't be sliding over the roadway. It should be a controlled roll. And just like when you walk, you're replacing the point of contact between your shoe and the ground. Your shoes should not be skidding over the ground. So since the point of contact is momentarily stationary, we call it static friction. I'll just call it lowercase f. Theta is that 15 degrees that they gave us. And you've seen this a bunch of times. That means this angle is also theta. So I've resolved gravity into a component normal to the roadway and parallel to the roadway. Let's make a proper free body diagram. That means get rid of the truck, just put a dot instead. Set up our coordinate system so it's clear to whoever's viewing this that the positive x-axis is parallel to the ramp and up the ramp, and then the normal axis I'm calling the y-axis. Because they told us that the truck's velocity is steady, we can infer that there's no acceleration before the piano falls off. And that means the net force is 0 along both axes. It's got to be true along the x and the y-axis. However, because we're dealing with static friction here, not rolling or kinetic friction, having thought this problem through already, we're not going to be setting friction equal to coefficient times the normal force. I should have prepared an equation for this, but I'll remind you that in general, static friction could be anything up to and including mu times the normal force. We don't actually have to we don't need to calculate the friction force in this problem. We can get away with not calculating it, as you'll see. So with the benefit of hindsight, I know that we don't actually need to write F equals ma along the y-axis. You may not see that at the outset of the problem. Sometimes it's best to just write Newton's second law along both axes and see what you can find out. Or, if you're in a hurry, just write the equation that you know you need to write and see if that's sufficient. I know I'm going to need to write the Newton's second law along the x-axis. So let's proceed with that. Here it is. That static friction force points up the ramp. The component of gravity parallel to the ramp points in the negative x direction, hence the minus sign. And since it's opposite theta, we go with mg sine theta. Also, I should point out, what is the cause, so to speak, of that friction force? If the driver wasn't stepping on the gas pedal, the car would just roll backwards. And that static friction force would just disengage. You probably would have some minor rolling friction, but that static friction force that points up the ramp, it kicks in because the driver pushes on the gas pedal and the engine via the drivetrain forces the wheels to rotate, I guess in this picture, counterclockwise. And in the act of rotating counterclockwise, they begin to push backward on the road and the road pushes forward. We don't have to worry too much about those details, but that's why the static friction force is there. Let me call this equation 1 so we can refer to it later. Now the piano falls off the truck, and the statement of the problem doesn't talk about this, but you have to imagine that at the moment the piano falls off, nothing changes about how hard the driver is pushing on the accelerator or the gas pedal. So the engine was providing a certain amount of, I guess you could call it thrust up the incline, and that amount of thrust, which we're calling F because it's a static friction force, is still present. So if you're getting the same push uphill, but the truck now weighs less because it's lost its load, of course there's going to be an acceleration now because the forces were balanced previously. Now they're not balanced because we lost some of that backwards force of gravity down the ramp. The mass that we're left with then is capital M, remember that's the total mass, truck plus piano, minus the piano which fell off. So this is the mass of the truck by itself. And I'm putting a blue bubble around that to emphasize that I'm about to let that be the M in F equals ma. When I say the M in F equals ma, don't be too attached to a particular letter M, just in the general sense, the mass in force equals mass times acceleration. So I'm reminding you here that we do in fact now have an acceleration up the ramp. So the truck is getting faster. Remember the rule, if acceleration points in the same direction as velocity, you know you're speeding up. They gave us the acceleration, it's modest. So previously, here was my free body diagram, and I did try to do it so that the proportions were correct. See how the normal force balances the component of gravity perpendicular to the highway? And I tried to also draw it so that the backwards component of gravity had the same length as the friction force up the ramp. And the reason for making these two lengths match was because previously there was no acceleration. The static friction was just great enough to overcome the backwards pull of gravity, but no greater than that. Now, I can reflect the change in the situation by shrinking these vectors. So if we just shed the mass of the piano, clearly the total gravitational force should be less than it was before. So I shrunk the hypotenuse here, and that means both components got shorter. And you'll notice I also made the normal force shorter because it only needs to balance this component of gravity. This component, the component of gravity down the ramp, also got smaller, and that is why there's now a net force up the ramp, because look at the length of the friction, the static friction vector. It has not changed, because presumably the driver needs time to react. He or she is still pushing on the gas pedal as hard as they were previously. So this vector minus this vector in the x direction still leaves you with the net force upwards, hence the acceleration. So let's rewrite F equals ma for this new situation. Total force equals our new mass times acceleration. The friction's still there. We've got the backwards component of gravity with the updated mass, and that equals updated mass times acceleration. Remember, capital M minus little m is, in fact, the truck's mass by itself. So here's our two equations. I've labeled this latest equation 2, and the rest is just algebra, as I like to call it. Now is the appropriate time to ask ourselves what we're solving for. I almost was tempted to solve for A, because often that's what we're doing. But actually what they asked us to find was the mass of the load that fell off the truck, which I'm thinking of as a piano. So we're really solving for little m. Let's look at these two equations and ask ourselves which quantities we know already and which we don't, because then we can identify how many unknowns we have. Now, since we've only got two equations, we better not have more than two unknowns. If you've got three unknowns and only two equations, you won't be able to solve for those unknowns. You would need a third equation minimum. So in the first equation, do we know how hard the roadway pushes on the tires? That's actually not given, so F is unknown. Do we know the total mass? Yeah, that's given, the 7,500 kilograms. We know 9.8. We know 15 degrees. So there's only one unknown in this equation, which means we could actually solve for friction right now and then plug that number in here. And then let's look at this equation. Once we evaluate F, it looks like the only unknown remaining would be m, the mass of the load, which I'm thinking of as a piano, because we're given the acceleration. So we could do it that way, but I'm going to take an even quicker route, because I'm recognizing if we multiply this equation by -1, take the top equation, multiply by -1, and then F turns into minus F, and this minus sign turns into a plus sign. Great, because now if we add these two equations, -F and F, those go away. So I'm going to, if this was a linear algebra class, you would call this a linear combination of the equations. Just add them up. Add up the left sides, add up the right sides. So the F's cancel. And take a look at capital Mg sine theta up top. We've got the same thing down here, capital M G sine theta, but with the minus sign. So those also go away. And look at this minus minus, that's really plus little m G sine theta. On the right side, 0 plus this just leaves us with the right side from number 2. We're getting close to the end here because we're solving for little m. So I'm going to take this term, minus little ma, I think, and put it over here. Right. So I'm collecting like terms. I've just collected everything on the left that has a little m next to it. And on the right side, all that's left is capital M times A. What's left but to divide by this quantity in parentheses? And there we are. There's our expression for the mass of the load, also known as the piano in my presentation here. Here's the numbers that they gave us. Plug everything in. Don't forget to make sure that your calculator's in degree mode if you're going to plug in 15 degrees. And before we plug in those numbers, it's useful to ask yourself ahead of time, do we expect this number to be bigger than 7,500 or less than? A truck should be heavier than the load that it's carrying. Well, I'm not sure that's true, actually. It kind of depends on, I really don't know. I bet there are trucks that can tow loads that weigh more than the truck by itself. But if it is a piano, it's certainly not as heavy as the truck. Here's what you get. That's if you round to 2 sig figs. I think that's all I have to say about this problem. What's on the next slide? Nothing. there was actually one more thing I should have said, which is this. Here's a reminder in equation form that the static friction force could be anything between 0 and the max possible value here, which would be mu times the normal force. If we had assumed from the get-go that this was equal to the friction force in this problem, we would have been led to the wrong answer regarding the mass of the load or the piano. In fact, we can even estimate what that max friction force would be. If I go back to this diagram here, 15 degrees is a small enough angle that we can really just pretend this roadway is flat and assume that the normal force is equal to the gravitational force, mg. Maybe you remember that more exactly it's mg cos theta, but the cosine of 15 degrees is probably close to 1 anyway. So mg, that's the mass of 7,500 times roughly 10. So that's going to be 75,000 newtons would be the normal force. And you may also recall that oftentimes static friction coefficient is close to 1. So that means that the max possible static friction force would be something like 75 kilonewtons. If we were to make that assumption and plug that number in for F, it just wouldn't work. It would certainly not be the same as mg's sine, because the sine of 15 is fairly close to 0. So there's no way mg sine of 15 is going to be equal to mu times mg cos theta. In this problem, the static friction is whatever it needs to be. It's whatever resulted from the driver pushing on the gas pedal and producing just enough force with the road, static friction force, to get the truck to go uphill at constant speed while it had the load.
Turn signals on.
This could be really bad.
Here we go.
Has a red light.
Oh no! Oh no!